Okay, today we're going to be talking about acid and base reactions. I prepared 2 lectures. That's the one we're doing on Wednesday, and what we're going to be doing in lab on Thursday. Today is on chemical reactions. So a chemical reaction is when you have 2 molecules, or it could be 2 atoms, or more, that recombine in some fashion. So on the screen here we have an example of a chemical reaction where we have hydrogen molecules, so that's H2 is a hydrogen molecule, and oxygen molecules, well, in the picture it's just one, and then they undergo a chemical reaction. The molecules break apart and reform differently. And so in this case, it's forming 2 waters. Notice it says here balanced. One of the important things we're going to learn today is balancing equations. If you look at the homework that's due on Wednesday, you have to balance a number of reactions. So what does it mean to be balanced? I have a bunch of slides coming up on this. I'm going to explain it now. So when we get to those slides, I'll go quickly through them then because I'm explaining it now. So a chemical reaction is balanced when the number of reactants is the word for the things that are going to undergo a chemical reaction, are equal to the number of the same types of each atom in the product. So in this example, if I look at the reactants, the best thing to do to just be safe is to count them up. So I have 2 H2 molecules. So that means I have a total of 4 hydrogen atoms. Since there's 2 atoms in each molecule and I have 2 molecules. So this number out front is telling us how many molecules are present. And then if we look at the next one, we have 1 O2 molecule. So how many oxygen atoms are in 1 O2 molecule?
2.
That's correct, 2. And so we have 2 O's. Now if we look at this side, we have 2 hydrogens per water molecule, and we have 2 water molecules, so that's 4 H's. We have 1 oxygen per water molecule and 2 water molecules, so 2 O's. Both of those are matching, and that's what makes it balanced.
Isn't that just so much fun?
Actually, I always liked it because I just kind of saw it as a logic thing. Yeah. Although you can make a mathematical formula and solve it that way, which would probably be necessary for complicated cases. So we have what's called the law of conservation, or law of mass conservation, which of course is untrue. Mass is not conserved, but the number of nuclei, that is the number of each type of atom, is conserved in a chemical reaction. So no atoms are gained or lost during any reaction is a true statement. Oh, I forgot to make more of those. I got to do that before we actually run out. So here's our first clicker question.
Wow.
Is this reaction balanced? Yes or no? So it's a simple question as far as, we have 2 options, yes or no. And each color is an atom. So you have green, red, let's call that magenta, and blue are the different types of atoms involved. And remember the www.
The additional blue ones come from on the right side.
Okay, well, then you get a chance. So.
Yeah, so if you put no.
Okay, well, I'm putting no.
Did it not take it?
I don't know.
I only have one. I think she already answered.
Yeah.
Okay, well, I will take your verbal answer. We had 1 each. So what was the key for an equation being balanced?
The same ratio.
Same, no, not ratio, same number of each type of atom before and after. So on the left-hand side, how many greens do we have?
2.
2. On the right-hand side, how many greens do we have? Okay, so those balance. Reds, how many reds do we have on the left-hand side?
So they're, two.
How many reds do we have on the right-hand side? Okay, we got a problem, don't we? The answer is no. I don't need to go further. If we go further, we'll see that the blues, we had 2 here, and we had 4 here. And I don't want to count the maroons.
Yeah, I didn't either.
Maroons or magentas or whatever we want to call that color.
I'm pretty sure there's more on this.
So it's not balanced because we didn't have the same number of each type of atom on each side. Good thing. So does that not make sense?
Yes.
Good. Is the following chemical reaction balanced? This doesn't show pictures. This has a chemical equation. This arrow means these things here form these things here.
Yes, it's oh, I'm sorry.
Just put it on your phone. And notice there's 2 yeses and 2 nos for different
My
reasons.
laptop is froze, so I'm verbally gonna say B.
I'm gonna try and type it in again.
Okay.
I mean, does it really, do I have to? Because, like, you'll know that it's
Yeah.
mine.
It's true. Yeah. I mean, you can say I want you guys to think about it.
Okay, well, I'm going with D.
Okay. So we had 1B and 1D.
Yeah.
This is working exactly the way it's supposed to work, right? As far as the woo clap. Okay. So let's look at this, and rather than saying who's right and who's wrong, we'll just figure it out. One of you is right. But I have to figure it out too. So we look at this and we say, okay, for it to be balanced, we need to have the same number of carbons, oxygens, and hydrogens in this case in each side. So we had, I'm going to change color here just because I'm tired of red.
I don't know why I love doing this so much.
We had carbons. How many carbons on the left-hand side?
1.
How many carbons on the right-hand side?
1.
Balanced.
Organization.
Okay. Hydrogens. How many hydrogens are on the left-hand side? 4. How many hydrogens on the right-hand side?
4.
4. All right. So far, so good. I changed back to purple. How many oxygens on the left-hand side?
4.
4. How many on the, oh, that was left-hand side, by the way. How many on the right-hand side? 4. So it has the same atoms appear before and after because it has the same number of carbons, same number of hydrogens, and same number of oxygens. So that's the correct answer. Now there was another yes because the coefficients on each side add up to the same. 1 plus 2 is 3, 2 plus 1 is 3. That was not material. What was material was how many atoms are present, not how many molecules. The fact that there were 3 molecules on one side and 3 molecules on the other was coincidental. And of course, the other ones, well, they couldn't be right because they say no. So once again, making sense? Counting atoms and molecules by mass. We know that if we have a hydrogen atom, look at the periodic table, it has an atomic mass of 1. Which means if I have a mole of hydrogen atoms, what will the mass of that mole be? 1 what? 1 gram. If it's a mole, then it's 1 gram. If it's an atom, it's 1 atomic mass. So the unit name is different. And that's how the mole number, the 6.02 times 10 to the 23rd, was chosen so that you would have that matching between atomic mass unit for a single atom or single molecule and grams for a mole of them. So we can take those and look at equations. So if I go back to this one, CH4, what is the mass of a methane? CH4 is methane. What is the mass of a methane molecule?
16.
Okay, tell us how you got that. You're right. 16, how did you get it?
1 carbon, 12,
Oh,
4 hydrogen, 4.
4 hydrogens, 4 times 1, so add another 4, so you get 16. Now, if it was a molecule, that would be 16 atomic mass units. If it's a mole, that's going to be 16 grams.
Yes.
So we can look at this and we can try to balance masses. We had 16 grams in the methane. Oxygen molecule, 2 oxygens. What's the mass of 1 mole of an oxygen molecule?
16.
That would be atoms.
Okay.
Since it's O2,
Oh. So, yeah.
32. So you have 32 grams for 1 mole, but look at that prefix 2. You have to multiply by 2 because if you have 1 mole of methane, we're going to have 2 moles of oxygen. So when we do the math, for the mass, we would have for 1 mole, we would have had 16 grams, and here we would have 2 times 32 grams, right?
Yes.
So if we add those together, 2 times 32 is 64. 64 and 16 is 80. So that's 80 grams total on the left-hand side. Now, if we go to the right-hand side, what's the mass of water? 1 mole of water. Water is H2O. So a single O is 16. 16 for the O, and then we have 2 H's. That's going to make 18. And then times 2 because we have 2 moles of water being produced for each reaction. 2 times.
If you want me to stop talking, you say something.
No.
I don't have a problem.
There's only 2 of you, and I want you guys, you're both participating. It's perfect.
Okay.
Carbon dioxide. We got an O2. O is 16, so O2 is 32 plus carbon.
12. Am I wrong?
32 plus 12,
Wow. No.
44 grams. So, of course, 2 times 18 makes 36. 36 and 44 makes 80 grams. So the mass is conserved because the atoms were conserved. And so that's why they called it the conservation of mass. The reason I said we know this is not true is because the mass of a proton depends on what atom it's in. A proton in hydrogen actually has more mass than a proton in iron. But that's a deeper level of physics. So, here is an example of doing the same problem with different numbers. So this was the picture that we started with, the reaction that creates water. So 2 moles of H2. And so going through the same process, an atom of H2 is 2 atomic mass units. So a mole is 2 grams, 2 moles, 4 grams. A mole of oxygen, 32 grams, and a mole of water, as we just calculated, 36 grams. And so if you add those up, 4 and 32 is 36. And then down at the bottom, it's showing the number of total molecules, which isn't really important now, is it? Notice the number of molecules here doesn't match up. You had 12 plus 6 is 18 times 10 to the 23rd molecules on the left-hand side, but only 12 times 10 to the 23rd molecules on the right-hand side. Question, Hannah. Alex, sorry.
I forgot. When you have the little suffix, I think, to
Yes.
to the number
Yes.
on the little one.
Yes.
Multiply or add because
Well,
both of those could be either.
yeah, if it's a 2, I understand. That's telling you how many they are. So
Yeah.
you multiply.
Okay.
So if it was H3O, hydronium, then you'd have 3 H's, so 3 times.
Yeah, I just hate when we do too. I just have everything to figure out
I understand.
on my own.
Now, reaction rates. A reaction rate is how quickly a reaction occurs. If a reaction occurs slowly, you might get impatient. If it occurs too rapidly, you might have an explosion on your hands. So reaction rates are important. You use batteries and things like your computer right now. Your computer actually has a chemical reaction going on in the battery that is supplying the energy you're using. And if that reaction were to go too slow, well, your computer wouldn't work, right?
Yeah,
So, what things do you think would affect how quickly a reaction goes?
Heat.
Okay?
Temperature? More specifically?
The word I wanted was temperature, but heat is a very relevant term here because you put in heat to make the reaction go because you're increasing the temperature when you put in heat. What's the difference? Putting in heat means you're putting in energy. Temperature is a measurement telling you about the average kinetic energy of the molecules. So both those answers are good answers, okay? Okay, so what's the next one? We have temperature or heat.
Time?
Well, we're talking about the reaction rate, so time is part of the answer.
Is
Mass.
Mass is actually not part of it.
like how much stuff you have of one thing or the other.
Concentration.
Yeah.
The concentration is another important aspect. Now there's three, so let's see. Order, concentration was first. Temperature was second. The last one is one you wouldn't have guessed. Catalysts.
I don't even. Oh.
Catalysts are things that lower the energy barrier to make a reaction occur. So they're not things that are part of the reaction, but they're chemicals that make it so the reaction can occur more readily with less energy involved. And so we have a couple of examples here. First, just what's the difference in temperature? Well, if you have a higher temperature, molecules are hitting each other more often and with more energy. And so the chances of the reaction occurring is more times per second. So that makes real sense. And of course, if you're breaking something apart, if it's higher temperature, the chances of breaking it apart are higher if they're moving faster. Then you have, was that one? That one was concentration. If you have more, they're going to have collisions more often because they're close together. Higher temperature, the collisions occur more often and they're more energetic, so they're more likely to break apart. Catalyst is the one that isn't so obvious. For a reaction to occur, there's always a certain energy barrier that has to be overcome. That is, you have to put some energy in to start the reaction. So we draw pictures like this for chemistry. Of course, I'm a physicist, I don't draw pictures like this. That shows the energy of the reactants initially and the energy of the products at the end. Now, in this case, the energy of the reactants is lower than the energy of the products. This reaction is not going to naturally want to occur because it's going to higher energy. It's kind of like saying, I'm going to take this from the floor and put it up here. Yeah, I could do it if I forced it, but it's not going to happen naturally. Whereas if this is up here and something bumps it, it could fall down to the floor all on its own. So this reaction could run the other direction okay, but it would never run this direction unless you're forcing it. But the key is this thing that's called E subscript A, it's called the activation energy. The activation energy is the energy barrier that has to be overcome to make the reaction occur. Now, heat was the word that Vanessa used. If you add heat, you're adding energy, so the molecules have more energy when they collide, which means that they can use that kinetic energy to overcome the activation energy, that barrier. So you add heat, and you can make a reaction occur that wouldn't have occurred, or if it's occurring, you can make it happen faster because you have an easier time getting past that barrier. But we were talking about catalysts. That's an important concept, but what are catalysts going to do? They're going to lower the size of that barrier. So here's an example of breaking up ozone. You know we have an ozone layer around the Earth. What is the importance to you and me as human beings of this ozone layer? Do you have any clue? If you have no clue, just say, I don't know.
Oh, it protects us from the radiation, the sun.
It protects us from the sun's ultraviolet radiation. The sun puts out light that's primarily visible light, but it also puts out ultraviolet light, and that ultraviolet light can damage our skin. It can cause bonds to break in the skin, And then once those bonds are broken, they can reform incorrectly, and we can form skin cancers. So the ozone is protecting us from that. How does it protect us then is the question of the chemistry section of this class today.
The oxygen.
Well, ozone is oxygen. Ozone has a certain activation energy, a certain energy that's necessary to break that ring. Notice it actually is a ring of 3 oxygen atoms, triangular molecule. And so how do you get this energy? It comes from light. Remember in physics when we talked about the energy of light, that it has these little particles called photons with energy h times frequency?
Yes.
Well, ultraviolet light is higher than visible light, which means the energy of the photons for ultraviolet light are higher energy. And so if you have an ultraviolet photon, it has enough energy to give a molecule that activation. So basically, here's what happens. You have this ozone molecule. Ultraviolet light from the sun comes to that molecule and it pops the band open, breaks the bonds. If you don't have ultraviolet light, it doesn't break the bonds. And so what it's doing is it's lowering how much energy they have to have from bouncing around because you're popping the bond with the ultraviolet light. And so this here is the energy to pop the bond that the ultraviolet light supplied. And then this is a much lower barrier than to continuing the reaction. So ultraviolet light from the sun pops the bond, and then, well, pops the 2 bonds, because you got 2 ozone here that react to give you the 3 oxygen molecules. So it's creating oxygen molecules from ozone molecules using the catalyst of the sunlight to give it the activation energy. So the actual energy these have before the reaction does not have to be as big. This here, I was actually pointing to this one. I shouldn't have. I should have just stayed on this picture. This here is showing what happens if you have chlorine atoms present. The chlorine atoms will make it so it takes a lot less energy to break those bonds, just their presence. And so if you have the chlorine atoms present, then you have enough energy in visible light photons to break the ozone ring. And so visible light will cause the ozone to break down if there's chlorine present, then the ozone layer depletes because the sun puts out a lot of visible light. And so we want that ozone there because it keeps us from getting skin cancer as often. But if we have chlorine atoms up there in the ozone layer, it's going to break down because the visible light is going to cause it to then, it's going to go visible light and break down quickly. And because of that, we as humans have changed our habits. We used to have a very good refrigerant, Freon. And that Freon was made with chlorofluorocarbons, things that had chlorine and fluorine. And the fluorine also catalyzes this, makes it so it takes less energy. And so if you have an air conditioner unit and it's leaking, and you know what they all do eventually? It would leak this Freon into the atmosphere. That Freon, where does it go in the atmosphere? It mixes. And so it mixes eventually throughout the entire Earth's atmosphere. And so you get some of it up there in the ozone layer. Sunlight hits it, you have a lot of ozone break down, and you have problems. So what does a catalyst do? Right, since that was the important thing I was trying to emphasize here. What does the catalyst do for a chemical reaction?
I mean, do you want the simple definition or the about me?
The one that works for you, the one you'll remember when it comes to a test.
It just lowers the reaction. Then that has to be over this.
Yeah, perfect. It lowers the reaction barrier. We call that reaction barrier the activation energy. But it lowers the reaction barrier. Now, another important thing, and I'm going to explain something on this slide before you answer the question, so it's not even open for answering yet. One of the things about a catalyst is it's not part of the reactants, and it's not part of the product. That is, you start with it and you end with it. So in this case, we started with, well, the last state is the most important one. It's not used up in the reaction. You have the same amount after the reaction as you had before. So in this, we start with O2 and 2NO. We end with O2 and O3. This is a reaction that's creating ozone. And the question is, what is the catalyst? What is the thing that is participating here, but is not changing the total amount that's present from the beginning to the end of the reaction?
And it's not active at the result?
Well, you have to have the same number of molecules of it when you started as when you ended. Okay, you're going to say A.
Yeah.
Okay, so we have two that said A. Yeah, look at that. So the key is have the same amount that we started with that we ended with. How many O2s do we start with? Okay, we started with one O2. How many do we end with? 0 O2s.
Oh. True.
How many NOs do we start with? 2. How many do we end with? It's tricky. We end with 2 because these went on to here. Actually, we started with 4 O2s, didn't we? We started with 4 O2s because we started with 3 O2s. Okay, I can do math, just not so well some days. So let me color code things so it's clear.
Okay.
So we start with this and this. We produce this, which just continues here, and it produces 2NO and 2O. But then the 2 O's go on to here, and we add in more O2 now. So actually, I should take off the green thing here. So green will be products in my diagram, and red will be intermediaries.
Okay, so you started with.
I started with everything that's in a purple box. So I started with 3 O2s and 2 NOs. And then everything in green is what I ended up with, 2 NOs and 2 O3s.
So the catalyst is
The catalyst is the one that has the same number beginning and ending. I should change to a different color so we don't confuse my careful color scheme.
Oh, so that was what the
The nitrogen monoxide, we started and ended with 2 moles of that, or 2 molecules of that, depending on which way you look at it. So that was the catalyst. And if you did the net reaction, it doesn't appear in the net reaction, which is what I meant by saying it's not part of the reactants or the products. It doesn't appear in the net reaction. The net reaction is going to be everything you started with to everything you ended with, removing the stuff that was present both beginning and ending. So this is the net reaction. The NO doesn't appear in that net reaction because it wasn't used up. So catalysts don't appear in the net reaction, but they're part of the reaction sequence. Making sense?
Yeah.
A little confusing? Energy. I'm trying to think of something you might have noticed where you see this happen. Have you guys ever used something like an epoxy?
tell you.
No.
Mm.
Well, an epoxy is a good example of this concept. If you take epoxy, you take two different liquids and you mix them together, and then it forms something that's hard and solid, and it gives off a lot of heat. It gets hot. Where's that heat coming out? Where's that energy come from?
Is that actually like one of those like packets that keep your hands?
Those are another kind of example. They're kind of an example. It's a chemical reaction that's doing it, but they're different than an epoxy because you can re-prepare it. Whereas with epoxy, you can't re-prepare.
Yeah.
But it's still an example of this. So where's that heat coming from with the epoxy or with a little hand heater thing that you break it from the hand?
It was added, like, mixing chemicals or something, and then we get excited.
It mixes chemicals, and when the reaction occurs, it gives off excess energy. It's what we call exothermic. Exo is going out. Now, you also have cold packs. I don't know how much athletics things you've done, but you can buy cold packs. They're just room temperature, and then you take them and you snap them, and all of a sudden they get really cold. That's the opposite. That's what we call an endothermic reaction. The end result, you had to put energy in, and it got cold. Because that energy was coming from the air around it to absorb the energy. So something that is exothermic is giving off energy. Bombs are very exothermic. They're giving off a lot of energy. Endothermic reactions, those aren't going to occur naturally. Those are going to be ones that we have to force some way to happen. Here is where it comes from. There's a certain energy associated with chemical bonds. The bigger this number, the stronger the bond is. So when you look at this table, what is the strongest bond in this table? The bond energy. The bigger the bond energy, the stronger the bond. Now, there's more than one example of nitrogen bonded to nitrogen. The one with the triple bond. These aren't molecules, so we just are looking at the bonds. So that's the strongest bond. What about the weakest bond? Oxygen. Well, there isn't really a name for them because they're not molecules per se, right? Because a single bond for the O's wouldn't be a complete. So, I mean, if this was O2, this is the actual O2 configuration, this one right here.
Yeah.
And so that's oxygen molecule. This one here would not be a molecule. It would just be part of a molecule. What were you asking? Reactions. Reactions are endothermic or exothermic. So we look at this and we're like, well, let's look at the nitrogen. If we can go from nitrogen with a single bond to nitrogen with a triple bond, the triple bond is so much stronger. Where does the energy go? If you go to a stronger bond, it's going to release energy. The stronger the bonds, the more stable it is. It's like going to lower elevation. So if I take a ball and it's on the top of the table and I drop it to the ground, it's going to give off some energy. It's going to hit the ground, do whatever it does to the ground. Let's think of rocks instead of balls. It doesn't bounce, it smashes them. So if I could take single bonded nitrogen and convert it to triply bonded nitrogen, I'm going to release a whole lot of energy. In fact, I would release 946 kilojoules per mole minus 159 kilojoules per mole. So if I can go from N3, or excuse me, NN to N triple bond N, that's going to be 159 kilojoules per mole to 946 kilojoules per mole. To calculate the energy difference, we take the final minus initial, that's the energy released, and we have 16 minus 9, 7, 8, 787 kilojoules per mole that are released if you can convert a single nitrogen bond to a triple nitrogen bond. That's a big amount of energy release, right? So how do we use that? Well, we use it in things like TNT. What does TNT stand for? Trinitrotoluene. Nitrogen is a major component in bombs because of that bond energy situation. So if a reaction has, if you add up the bond energies on each side of the reaction, if the sum of the bond energies on the left side, the reactant side, is smaller than the sum on the right side, the product side, then it's exothermic. It's going to give off energy. If you have stronger bonds on the final product side, it's going to be giving off energy. If you end up with weaker bonds, then it's going to have to absorb energy to make it happen.
Is that how anything to do with fevers? Like when you're sick, fever?
No, that's actually a different thing.
It kind of seems similar, so.
So here is yet another clicker question for you to answer out loud as you please. Use the bond energies below to determine whether this is an exothermic or endothermic reaction. Now this is going to take a while, right? Because you have to add things or subtract things. So how do you do it? Okay, what's the bond energy for the hydrogen? Then what? Then the chlorine, and what's it? So if we add those together, what does that give us?
661.
79. So our total bond energy was 679 kilojoules per mole on the left-hand side. What about the right-hand side? That's right. That's the trick on this one. It's 431 kilojoules per mole, but we have 2 moles produced for the reaction. And so then we subtract. So 862 kilojoules per mole minus 679 kilojoules per mole. Now, we finished our calculation and we can answer the question. Is it endothermic or exothermic?
Endo.
Why do you say endo?
I don't know.
I just lost my train of thought. The answer is exo. It's exo because you have stronger bonds in the end. The bonds in the end have a total of, if I started with 1 mole of H2 and 1 mole of Cl2, then I would have had 679 kilojoules of energy, of bond energy starting. And I would have ended with 862 kilojoules of bond energy in the end. I would have ended with more bond energy.
Yes.
But if you have more bond energy, it's held together tighter and it releases the difference. It sounds a little bit wrong because it sounds like you have more energy, like somehow you naturally made energy. But that bond energy is actually a negative potential energy. So it goes more negative, and the total energy has to stay the same, so you give off.
Can you give an example of another kind of bond like that?
Something that would be endothermic.
Yeah,
Is that
like a
exothermic?
problem like that. So I know what you're saying.
Yes, let's go all the way back to where it had an example that was that way. So not this one, that's exothermic there. Nitrogen and oxygen. So if I have 1 mole of nitrogen, so I have N2 plus 1 mole of oxygen, that yields 2 NO, right? So now we have to look at those numbers. Do I remember those numbers? Of course not. I'll write this equation on the page that has the numbers. N2O2 is 2NO. So erasing everything on here so we can start over fresh.
So 159 plus 130.
Hey, you're not supposed to go faster than me. Okay, so N2 is 159. And O2 is 138. That's what you said, right?
Mhm.
And so if we combine these, what does that give us? So we start with 297 kilojoules. If we start with 1 mole of everything on the left-hand side, we have a total of 297 kilojoules of bond energy. Now, if we go to the product side, we have 2 times, and where's NO? Yeah, that's actually what it is. It's kind of weird. You formed a double bond there, and the nitrogen, it likes to form more than that. But I'm pretty sure it's a double bond, like you said. So it's going to be 2 times 631 kilojoules per mole. That actually can't be it, because that would have been exothermic, not endothermic.
Yeah.
And the picture showed endothermic. So honestly, I wish I was a chemist. I'm going to actually look up real quick.
Yeah, I was like, what is the difference between this and that? Like, I'm confused.
Nitrogen monoxide. It shows it. Wow. It shows it with a kind of triple-ish bond, which is not present here. Bond energy. So I'm looking up the bond energy for nitrogen monoxide, and it is 68 kilojoules.
Okay, so it's going to be negative.
Wait, 60. The problem I'm looking at is actually not giving that actual number, which makes me sad. So we don't have the bond energy for this. Here's what this tells me. It tells me that there is a net, where is it? A 180 kilojoules is the net. So 297, if we take 180 minus that, then that's going to be 117, which makes this 58 and a half. Going backward with my numbers from the answer. Which I wish that we had those in the table, but it just doesn't have this here, the bond energy.
So how does that end it?
So you started with a higher bond energy, 297 kilojoules per mole. You ended with a weaker one, 117 kilojoules per mole. So they're not held together as tightly. If they're not held together as tightly, that means you had to net add energy in.
Okay.
So you had to add 180 kilojoules to make this reaction occur.
I think I'll get it.
Or that's the net energy difference that you had to add. We've already done this calculation. Don't need to look at it again. So, entropy. Now this one here, I'm a physicist, I take a little exception, but I've got to show you some of how chemists view the world. It says that chemical reactions are driven by entropy. What is entropy? Well, great question. The common answer that you learn in introductory classes, entropy is the amount of decision. And that the second law of thermodynamics says that every naturally occurring thing will result in an increase in energy. Well, everything that occurs actually will result in an increase in energy for the universe. So increase in disorder, if you will. But what that disorder actually means is not what most people think it means. The disorder is telling you about probability. And so higher entropy actually means more probable. And so everything that occurs is going to result in a more probable outcome and not a less probable outcome. So when you have something that has an increase in energy, or entropy, it's going to result in an increase in heat divided by temperature. So the words here are trying to give you feelings of how it works. So it says it's the natural tendency of energy to disperse from where it is concentrated to where it is diluted. Now, me being a physicist, of course, I have different ways of looking at this, and here's my great example for entropy. We have a lot of nitrogen and oxygen molecules in this room. There is nothing in physics and chemistry that says that we can't have all of those molecules in little rows of block up in the corner. They just naturally all go to the corner and freeze up there. There's nothing that says that can't happen, except it's so unlikely, because you have all of the energy concentrated in one place instead of spread out. And so nobody ever expects that to happen. None of us are worried about suffocating because all the oxygen went to the corner. Because that would violate the second law. That would be going to a lower entropy state instead of a higher entropy state. So if I started with all the molecules up there, the high entropy state, they would naturally disperse and spread out. Now, this is, of course, the last minute of class. I have to bring this around to us being a Seventh-day institution. A lot of us, I certainly one of them, believe in creation. And some people, of course, believe that life began through evolution. And you will hear arguments about entropy when people are trying to discuss this. And people will say, well, it's a violation of the second law of thermodynamics to go from a less organized system to a more organized system. That is to go from a higher entropy to a lower entropy. But the problem is, you can always control a system, so even though the net outcome is greater entropy, in this region it's lesser. An example would be freezing ice. You can freeze ice, that's lowering the entropy of the ice. The ice is becoming more organized, less random, and so that's a lower entropy. But it's at the expense of something else. So it's not in that sense a violation of the second law of thermodynamics. It's not an entropy thing that says, oh, it can't happen. But if you remember the other side, what entropy really is having to do with probability. It's saying more probable things happen, not less probable things. And the probability of creating these, the chains, first you have to create amino acids, and then you have to create polymerized chains, and from those you have to do some more other organizational things. The calculations for the change in entropy, the probability, are astronomically slim. The chances of those occurring is very, 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 very minute. And so in the sense of the probability, the entropy argument does work. It's really, really improbable, and the second law says it's just not going to happen for life to evolve naturally. And people who say that God can't interfere with life on Earth, may or may not exist, but he can't interfere, that's what we call naturalism. Say, well, since God didn't do it, that's my preconceived notion, then even though it's impossible to happen, it must have happened. And that's ultimately, it's a theological debate when you get down to it. both people who believe in evolution and people who believe in creation. They're not really arguing science there. They're arguing theology. Okay, have a great day. I'll see you again on Wednesday when we will talk about acids and bases, and then lab on Thursday when we'll be doing experiment with acids and bases.
I have a question.
Fire away.